My name is Lidia Leoni. I'm one of the CRS4 directors. I'm responsible for the bioscience and computational infrastructures, smart project, and quantum computing sector. First of all, I wanted to thank the organizer for allowing us to participate in this fantastic day, dedicated to promoting the public understanding of quantum science and technology around the world. CRS4 has decided to participate in World Quantum Day because we believe it is an excellent opportunity to share our work and our vision on quantum computing and the future. The title of our presentation is World Quantum Day at CRS4, Leveraging Quantum Computing for Real-World Application. Now, I would like to share my presentation. Yeah, I don't know if you can see. Okay. This is the program for the day. We have decided to share our problem that we are facing. I want to make some consideration for the future. Given the time, we will not be able to go into details, but please contact us if you want more information. It will be a very big pleasure to discuss it together. Now, just a few words about CRS4. The Center for Research, Development and Advanced Studies in Sardinia, born in Cagliari in 1919, on the initiative of the Sardinia region, under the guidance of the Physics Nobel Prize, Carlo. CRS4 is a private research center under the control of Sardinia region, and that is the sole partner of CRS4. Our goal is to study, develop, and apply innovative solutions with a multidisciplinary approach using highly specialized skills and knowledge. Scientific research and technological development are the basis of our activity on some major topics, which is CRS4 pursues excellence: artificial intelligence, big data management, high performance and quantum computing, applied on focus on information society, bioscience, aerospace, visual computing, energy and environment, and smart city project. The center manages a supercomputing center equipped with both a data center capable of hosting up several petabytes of information and a latest generation HPC infrastructure, among the most powerful in Italy. Why is quantum computing important for apply R&D in HPC center? Classical computing processes data is a binary space which limited the volume of data it can handle and the decision it can produce. Quantum computer, however, use a multidimensional computing. Classical proceeding checks each combination of data one at a time to arrive at the correct results. Multidimensional processing is layered, unlike the binary approach to serial processing which use bits. This speed up the delivery and accuracy of calculation and improve the diversity of results. In short, quantum computing can deliver better quality results faster. Currently, many of the uses of quantum computing are experimental or hypothetical, as we are still in the early stage of learning how to implement quantum computing scale. But as the technology develops, organizations shouldn't be ignorant of how they can use it. The CRS4 has always used large computers to solve different types of problems. And for about 3 years, we have created a group that deals with quantum computing. Now I leave the floor to Giuliana, Siddi, Moreau, and after our colleagues. See you later for the final conclusion and consideration.
Thank you, Lydia. Let's start now with a gentle introduction to quantum computing. As we are an organization that carries out applied R&D, our perspective will focus on what we can be used so far to start harnessing quantum computing, in QC for short, in real-world application. So now allow me to share my video, my PowerPoint presentation. Just a moment. Here it is. Can you see my screen?
Yeah.
Okay. So, now let's start with this short introduction. And let's see, for instance, what are the units of information in quantum computing, as we are expected to give some highlights on quantum computing. Let's start from what we already know. A classical bit is binary. It can take one of two states. It can either be state 0, let's say a coin side like head, or it can be state 1. For the same coin, it's the other side, tail. The quantum computer is built from logical elements called qubits, which is the short for quantum bits. A qubit is binary in the sense that it's realized using a quantum coherent two-state system. And it can be set in state 0 or in state 1 that corresponds to the call of the Bloch sphere we can see in this nice picture. A qubit can also be a quantum superposition state, that is a single state, but it carries aspects of both state 0 and state 1 simultaneously. All points in the surface of this Bloch sphere represent a superposition state. Superposition state results in probabilistic measurements, meaning that if we have, say, an equal superposition of 0 and 1, and we measure the qubit, we have a 50-50 chance of measuring state 0 and a 50-50 chance of getting state 1, like a toss of a fair coin. When we measure the qubit, we destroy the superposition state. We have another special feature of the quantum world that is called entanglement. We can create a strong correlation between a pair or a group of qubits in such a way that the quantum state of each particle cannot be described independently of the quantum state of the other particles. The pair behaves like a pair of linked coins that drop on the same side simultaneously. When we measure both members, we find that the results always agree. And we can get the results even if great distances separate the two systems, and the measurements are performed nearly simultaneously. So, how many states can we represent with n qubits? A classical computer can represent only one of these n-bit states at a time. Processing multiple n-bit states can either be performed sequentially in time or in parallel using additional copies of the hardware. This is classical parallelism. In contrast, the qubits in a quantum computer can be set into a single superposition state that may simultaneously carry aspects of 2 to the power of n components. This enables two uniquely quantum mechanical effects: quantum parallelism and quantum interference. And this is the road. How do we represent the logic structures in QC? Classical computers perform arbitrary Boolean logic with a small set of single bit and 2-bit logic gates. As far as universal quantum computation is concerned, it can be built from a small subset of these types of single or 2-qubit gates. A universal state gate set enables us to perform any type of algorithm, quantum or classical, on a gate model quantum computer. Single qubit gates are unitary quantum operation on single qubits that can be represented as rotation in the block sphere we saw before. Two qubit gates are unitary quantum operation on two qubits. When this gate cannot be written as the product of two single qubit gates, they are called entangling gates, and they exploit entanglement to create strong correlation between qubit states. In quantum information theory, a quantum circuit is a model for quantum computations, similar to classical circuits, in which a computation is a sequence of quantum gates, measurements, initialization on qubits to known values, and possibly other actions. What are the current limitations of QC? Currently, we are in the noisy intermediate scale quantum era, and quantum computers are affected by noise, by errors. They are not fault tolerant. Over time, the qubit begins to interact with its environment. And as the time goes on and the qubit is subject to more of this environmental noise, eventually we cannot longer recognize its state. And the quantum information is fully lost. This behavior will be visible as error when you do calculation. Here we see in the image that there are two processes by which a qubit loses in quantum information. The first is called energy relaxation. That is a qubit in its excited state tends to relax back to its ground state 0 by emitting energy to the environment. And on the block sphere, you see that the qubit spans from South Pole to the North Pole. For this energy loss. Another way a qubit loses information is through the coherence. A qubit starting on the equation of the block sphere might move along the equator away from its original position. This is called dephasing. And when it does so, the qubit experiences noise that alters the qubit state in a way that we didn't anticipate. And to prevent this behavior, there are techniques such as error mitigation that reduces error that occur during computing, and error correction that restores the computation after an error occurred. They are among the most active area of research at the current day. What problems can be solved in QC, in quantum computers? Quantum computers are ideally suited to solving complex problems, which are hard for classical computers. If we have to measure how efficiently a computer can solve a given problem, this efficiency is determined based on how the computational resources grow when they are needed to solve this problem. And one of the main reasons of the current interest in quantum computers is that certain problems can be solved in polynomial time on a quantum computer, even though the best known classical algorithm for the same problem requires exponential or sub-exponential time. So a quantum computer is an accelerator for only some types of problem, not a general purpose computer. The challenge now is working out what quantum computers can be best used for. As with any new tech, there is no easy answer. Anyway, quantum computers will be particularly good at tackling certain problems that are difficult or even impossible for classical computer to solve, like quantum chemistry. And powerful, cost-effective quantum computers will be also great at solving special algorithms, at using special algorithms to solve complex optimization problems, such as scheduling, routing, and logistics. And these algorithms involve seeking the optimal solution from lots of possibilities. And even AI will be sped up by quantum computing, as there are new formal proofs that training in a quantum neural network requires only a small amount of data, in contrast with classical computing huge appetite for data and machine learning. Quantum computers can be applied to many types of simulation problems. The challenge is that many of these problems require a large number of resilient qubits, and such a large-scale quantum computers are still likely some years away. Before we get to the point that we can simulate system entirely on quantum computer, there are room for hybrid classical quantum systems to hold a quantum advantage over purely classical algorithms. One example of that is called a operational quantum eigensolver. Classical quantum computers are passing information back and forth through the simulation like a Pong match. Therefore, the quantum computer is acting as a coprocessor. It need not to be coherent over the entire duration of the simulation, but only over the period of time it takes to produce a single trial state, obtain the necessary observables to calculate its energy. And this approach allows useful computation to be done in the nearer term using less reliable noisy qubits. What types of quantum computing can we use by now? So if we restrict ourselves to universal quantum computer, there are a variety of physical systems that have been proposed as qubits for quantum computer. There are many ways of building a quantum coherent two-state system. In spin qubits and in these centers, we are exploiting electrons and nuclear spins. For ion traps and neutral atoms, we are utilizing atomic states. Superconducting qubits are based on electrical circuits, such as nonlinear oscillators that behave like atoms. There are other qubit modalities, such as topological qubits, that are currently under study. But we cannot see any accessible hardware to test them. And there are, aside from universal quantum computing, we still have other possibilities to explore. Analog simulators are quantum computers that can simulate a quantum system using both digital gates and analog evolution. Alternatively, the qubits themselves and the way they connect to one another and the strength of those connections can be designed to emulate a system behavior. So we can model an Hamiltonian on an analog QC, tuning all these parameters and find a ground state. Quantum annealer, also known as Adiabatic quantum computer, is a different type of computer that addresses classical optimization problems by mapping them onto a set of interconnected qubits. And then they search for a solution that minimizes the total energy. And the idea behind quantum annealers is that we have a quantum system that is governed by one Hamiltonian, and we can transfer the system to another Hamiltonian by changing the system parameters. And if the transition is done slowly enough and the system has no noise, the computer will remain in its ground state throughout the evolution. And we have also photonic quantum computing with linear optics that use photons as qubits. Photons have the advantage of minimal decoherence. However, they don't naturally interact with one another. So in order to make 2-qubit gates, an effective interaction need to be induced. Photonic processors use Q modes, which are a different way of carrying and manipulating quantum information that qubits. A Q mode is a quantum mechanical harmonic oscillator represented by a light beam. And the qubits in Q modes is not unique. There are many ways of doing that. And the way in which Q modes have their state space structure is completely different from qubits. That's why this realization is still considered a chapter apart. So consider all these realizations. There are many parameters to take into account if we have in mind to address a specific hard-to-solve real-world problem with quantum computing, and in general, hybrid computation. As the hardware landscape is really heterogeneous, and the number of qubits in characterization is low, we need to look for the best fit of the algorithm we are developing versus a target quantum computing realization. That's why that's what we are going to see in next presentation of my colleagues. So I'm done for now. Thank you again. Thank you very much.
Thank you very much, Giuliana.
Thank you.
Thank you. So I leave the floor to Lorenzo Pisani. Thank you, Lorenzo. It's your time.
Thank you, Lidia. Hi, everybody. I will present a particular application of quantum computing. And let's share the screen. Okay. In particular, I will present an application on the optimization of multi-tower solar plants. What's the motivation of this study is everybody knows that many considers solar energy as the primary energy source in a potentially carbon-free society. One of the main problems of solar energy is its low energy flow, which implies if you want to use it as an important primary energy source, you need a large territory. We use a large amount of territory to collect enough energy. That's why it's very important to maximize the efficiency of the collection of the solar energy. For what concerns solar thermodynamic systems, solar tower, which concentrate where the mirrors concentrate the solar energy on a single point, a focus point, are more effective than linear concentration system, because in a single point you can get higher temperatures and the thermoelectric conversion is more efficient. Solar tower can be assembled in a modular way in multi-tower systems, and multi-tower systems are more efficient than single tower one because of optical reasons. You see in this picture we have a real plant which has been realized in Australia, and here you see we have here 5 towers with 5 mirror fields, and in this case each field or mirror point on the relative tower. We can improve the efficiency of the system if we allow the mirror on a field to point the reflected energy to another tower. By this way, we can improve by a few % the efficiency. This this case, this problem can be considered as a discrete variable optimization, as each mirror has to choose among the 5 towers. So there is a discrete choice. And in principle, this problem can be afforded by adiabatic quantum computers. Why to use quantum computers? We see here an example of a realistic system with where the black dots represent the towers and the colored dots the mirrors. In this case, the blue dots points the reflected radiation to the left towers, while the orange dots reflects the sun radiation to the right towers. In this case, we have more than 3,000 mirrors, and the number of possible configuration grows exponentially with the number of mirrors. In this case, we get a number of possible solution which has more than 1,000 digits. So you know now why we mean to use quantum computers, because the complexity of the system is, or the problem is enormous. Well, at CRS4, we have developed a model which is able to optimize realistic multi-tower system in a few seconds. We can deal problems with the different number of towers we have in this figure, 4, 5, and 9. Increasing the number of towers, the complexity increases, but we are still able to manage these problems in a few seconds. As you know, the direction of the sun changes with time. And all the figures you have seen in the last slide was with the sign at the zenith. But if you change the direction, the optimal configuration changes. Here the sun is at zenith, here it's at 30 degrees, here is 60 degrees. And as you can see, the optimal configuration changes with the direction of the sun. So this means that with time you have to do again the calculation, the optimization, and decide in real time to which tower each mirror should point the reflected radiation. So you need to have a fast optimizer, because you have to follow the change of direction of the sun. In this case, we are able to perform the optimization at computational time 13 seconds. So it's fast enough to follow the sun. I conclude by saying that reduction of greenhouse effect is one of the big challenges of our future, and solar energy could become the primary energy source. We have seen also that multi-tower solar system with the aimed tower optimization may become a key technology for the achievement of solar thermodynamics plants, but still requires efficient optimization methods. We at CRS4 we developed a method which utilizes adiabatic quantum computing for real-time optimization. This method could enable the achievement of multi-tower technology. This is our hope. I have to thank Sineca for making us available the computing facility, and the Sardinia region for financial support.
Thank you very much.
Thank you. I thank you.
Thank you, Lorenzo. Now it's time to Erminia. It's time for Erminia Leonardi, please.
Thank you, Lidia. Hi to everybody. see. One moment, please. Okay. Well, let me introduce in this brief talk the activity on quantum computing and chemistry at CRS4. This is one of the lines of research recently opened within our quantum computing group, and it is with the implementation of computational models for the calculation of the electronic structure of molecular systems on quantum machines. This is a topic on which there is great attention from the scientific community because computational chemistry presents itself as one of the most promising application sectors on quantum computing. In fact, quantum computers already allow to perform studies in the field of semiconductors, for example, for the development of semiconductors at room temperature, starting from the search for new materials, the development of eco-friendly fertilizers, or for the fight against climate change, identifying new ways to remove carbon dioxide from the atmosphere. It is precisely on this last research topic that we have focused our interest. In particular, we were inspired by the latest proposal from Deloitte 2023, which launched a challenge on this theme of climate change, stimulating participants to use quantum computers to study the behavior of materials able to capture carbon dioxide from the atmosphere. This is really a strategic research topic, since a global energy transition on low carbon emissions is urgently needed to limit global warming below 2 Celsius degrees in the last few decades. We have to consider that in 2013, the International Energy Agency had hypothesized a scenario for reducing CO2 by 2050 with the contribution as large as 19% of carbon capture technologies. But unfortunately, we are lagging behind, given that carbon capture technologies currently contribute only by 0.1%. The work we are carrying out at CRS4 implies the use of quantum computer algorithms and simulators to describe the interaction of CO2 molecules with metal organic frameworks. In this approach, we consider a fragmentation strategy and concentrate our attention on the behavior of the absorption site, which will be simulated using both classical and quantum computation. In particular, we started from the calculation of the potential energy surface describing the interaction of the metallic charge atom with a charge +2 of the metal organic framework with a carbon dioxide molecule. At present, we have considered the interaction of magnesium +2 or zinc +2 cations with the carbon dioxide using different approaches, like the unitary couple cluster that truncated to single and double excitations, but also full configuration interaction restricted to a set of selected orbitals. Once the answer of the electronic wave function is defined, it can be variationally optimized by quantum computing techniques, such as the variational quantum eigensolver, which is an hybrid quantum classical algorithm in which a quantum computer is used to evaluate the expectation value of the Hamiltonian of a given quantum state, while a classical computer variationally optimizes the energy. And the molecular orbital have been obtained by standard methods such as the Hartree-Fock approach, and the orbitals used in the calculation limited to a subspace of the full orbital space. This choice is done on the basis of an energy criterion, but also on a more sophisticated one. This orbital subspace is used to estimate the electronic dynamical correlation, thus reducing both the size of the system and the qubits needed in the quantum circuit. Even if the study is still in an initial stage, a few relevant achievements emerge from our exploration. First of all, we have found that the use of two small atomic basis sets, such as the STO3G basis set, suggested by Deloitte in the document describing the challenge, can be inadequate for the study of systems containing transition metal atoms. Indeed, the ground state of transition metal atom, both neutral with a 2+ charges, incorrectly predicted using this basis set, even at full CI level. Therefore, we have decided to use a more sophisticated basis set like the 631G or even more complex one. Moreover, the full CI results on a set of possible definition of the active space show that the energy criterion for the selection of the molecular orbitals defining the active space is not optimal, especially when rich atomic basis sets are used. Indeed, from one side, using this criteria, the amount of dynamical correlation energy captured by the active space is not maximized. On the other side, this procedure is prone to a sudden variation of the nature of their active orbitals when the distance between the fragments is modified, with a consequent sudden variation of the energy. We have therefore devised a computational strategy for an alternative identification of the molecular orbitals. In particular, we have used the natural orbitals to define the active space, which allows both to catch a large amount of the dynamic correlation energy and to guarantee a uniform description of the system along the potential energy curve. I conclude this presentation remarking that this is a work in progress, where, among the others, more effective definitions of the wave functions need to be explored. And that's all. And thank you for your attention.
Thank you, Erminia. Okay, I leave the floor to Carlo. Please, Carlo, it's your time.
Thank you, Lidia. Thank you. I'm Carlo, and in the next few minutes, I will briefly show how the field of quantum computing can be accessible even to people not directly interested in writing quantum algorithms to resolve scientific problems. In fact, also technology enthusiasts curious to explore this fascinating field can put in practice their skill in classical software development and system administration. Let me start with the presentation. It's okay. Can you see the presentation?
Yes.
Yes, very good.
Thank you. Okay. First of all, is worth noting that despite quantum machine and the quantum software simulators are currently limited in resources, the former due to technology that is constantly advancing, and the latter due to the limited number of qubits that can be simulated. There are numerous resources currently available, both the hardware and the software. And in the hardware and software side. There are different technologies, as already explained Giuliana in a previous talk. There are different technologies to implement qubits. Each one presents different manufacturers that still compete for visibility and leadership. Technology are superconductor, trapped ion, neutral atom, photons, and other under development. But in this set of manufacturers, there are at least one offers to users a wide range of dozens of different quantum computers. Moreover, several other manufacturers provide their users with various quantum resources. So we have access to an interesting variety of different machines. Even from the software standpoint, we have several options to choose from. Typically, a manufacturer provides their own dedicated software development kit, or SDK, to interface the software for utilize their machine, to interface with and utilize their machine. In fact, however, in many cases, they also guarantee compatibility with SDK from other manufacturers. And this heterogeneity of both hardware and software solution enable benchmarking of quantum computing application, allowing developers to compare the performance of their algorithms on different resources over time. So while there is no best quantum computing solution currently, checking the code performance on different platforms and using different SDK periodically is a wise choice for developer. However, this kind of comparison is challenging due to the complexity of multi-platform work, and this complexity can additionally complicate the work of researchers and developers. So classical software can be particularly useful in this case, serving as a natural bridge between the different hardware and software solutions, effectively hiding the underlying complexity. We are not referring to high-level services such as Amazon Bracket or IBM Quantum Experience or similar platform that already popular and used among quantum programmers and scientists. Instead, we refer to a low-level software that may not be graphical, but highly customizable through the platform API and the libraries included in the software development kit, or created ad hoc as necessary if needed. From an architectural perspective, when compared to traditional architectures of classical computers, quantum computers are relatively simple machines. They have a small number of qubits and a limited set of properties to consider. I'm speaking about physical properties. And they don't have a complex operating system to learn and manage. And all of this makes them simple in nature with fewer complexities to deal with. And by using routines available in the software developed SDK and referring to classes and method present, it's possible to gain a deep insight into the resources and their state. We at CRS4 are actively researching and developing advanced tools to streamline the work of researchers and scientists engaged in quantum computing, with the goal of making their task more efficient and user-friendly. Additionally, our objective is to provide tools for analyzing and comparing results across different quantum resources. Okay, this is my presentation. Thank you for your attention.
Thank you very much, Carlo. Okay, now it's your time, Giuliana. Thank you very much.
Hello again. Thank you. I'm really proud to be here in this wonderful venue. And now let's move on some quick highlights on adiabatic quantum computing for optimization problems. It's a list of studies we are carrying out, and I will provide some quick highlights. May I share the screen? Okay. Okay, can you see my screen? I think, oh, it's okay. Okay, so let's start to focus on two different studies stemming from non-convex optimization addressed with adiabatic quantum computing, also known as quantum nonlinears. Now we can see two case studies from two different domains. One is gravity data inversion, and the other is the application of optimization to smart cities. First off, let's give some problem setup. Convex optimization is a subfield of the mathematical optimization that studies the problems of minimizing convex function like we see here in the left picture over convex sets. Many classes of convex optimization problems need polynomial time algorithms and are addressed in a great way with conventional solvers. So we don't care about convex problems that are already being solved in a smart way. However, a non-complex optimization problem is any problem where the objective or any of the constructs are non-convex, are as pictured in the image on the right. Such a problem may have multiple feasible regions and multiple locally optimal points within each region. So if you use a gradient-based solver, you get trapped in a local minimum and you cannot attain the global minimum. And so it can take exponential time in the number of variables and constraints to determine that a non-convex problem is infeasible, or that the objective function is unbounded, or that an optimal solution is the global optimum across all feasible regions. And the optimization may also require an initial guess, a starting point, which is critical and can greatly affect the objective value of the local solution we obtain. And little information is provided in advance about how far from the global optimum the local solution is. So we have many domains in which non-convex optimization arise. Also in machine learning, we have many non-convex optimization problems that we have to face to train our AI. And it's likely that quantum methods can efficiently solve certain hard optimization problems where classical approaches fail, because, as we see before, we got different way of exploring the state space. And this is the starting point of our studies. So, as far as the first time is concerned, we aim to cast an optimization as an optimization, the solution of an inverse problems that stems from geophysics, like gravity data inversion. What's an inverse problem? Well, inverse problems mean to identify the causes from the effect. In our case, we want to reconstruct the subsurface model using data measured by the sensor placed at the surface. Direct problems are in general well posed. You have a unique solution, a stable numerical method, and polynomial time complexity. If the information given by the measurement is incomplete across the boundary, the inverse problem is ill-imposed. So we have multiple solutions. And also you can get deterministic polynomial complexity. That means that you can only verify in polynomial time that a model is a solution of your inverse problem. But finding a good solution for the inverse problem can need exponential resources. So the research question that underlines our activity is then, is there a different way of stating an inverse problem utilizing quantum processor in order to get a valuable solution in faster? So for our study, we casted our inverse problem as a minimization problem, where the direct problem is embedded into the quadratic and constraint boundary optimization linear quadratic terms. And we solved it in a quantum annealer. The objective function of the optimization is not convex, and it features many local minima. So our aim is to possibly attain a global minima, or at least a good local minimum. Exploiting the interesting properties of quantum annealing, that is quantum tunneling and adiabatic evolution. And this is an ongoing research, and we are currently assessing this approach on more complex model and then static contrast characterization. For the second case study, CRS4 provides an in-house operational control platform to support smart city management, decision-making, spatial development, planning, and emergency response. This is a great playground for non-convex optimization, as we have lots of data and lots of problems that can be solved at a smart city scale, such as scheduling, routing, and logistics, in which quantum computer might find solutions that attain the global minimum for the function we are optimizing, or at least something closer to the global minimum. Currently, quantum annealers provide a number of available qubits in which this problem can be addressed, and they do not allow a formal claim of quantum advantage. Anyway, analog quantum computing and variational quantum algorithms such as QAOA might provide interesting solutions as the realization becomes scalable and usable for this purpose. These solution approaches will be investigated in close collaboration with the smart project technologists that developed this in-house platform during an ongoing large technological problem headed by the municipality of Cagliari. And finally, we acknowledge the Seneca Award under the ISCRA initiative because we have the availability of quantum computing, adiabatic quantum computing resources through it. And we thank as well the Sardinia Regional Authority for financing our studies. Thank you for your attention.
Thank you very much. Thank you very much. Now I think it's time to conclusion. You have to please give me the screen. Thank you very much.
Lydia, we have still to present something about our HPC infrastructure. It's now the time for our virtual lab tour.
Okay, it's time, please.
So may I share the screen for a quick virtual lab tour? So, as you can see here, this is our virtual lab tour. We don't have quantum computers so far, but we have a massive HPC infrastructures that you can see here with a data center capable of hosting up to 6.3 petabytes of information. And we use this HPC infrastructure for running quantum computing simulators that are essential for prototyping quantum circuits and algorithms. And so we are exploring the performance of the quantum algorithms in a noiseless playground and under realistic device noise models before experience their behavior on real quantum computers. And so there are two quantum computing simulators two types of quantum computing simulators we can run here in our HPC infrastructures, GPU-based and parallel HPC simulators. And the boundary between these two types is thin, as we can also perform multi-GPU simulation, exploiting multi-threading, parallel libraries such as OpenMP, and message passage like MPI to split the calculation among multiple HPC nodes. So we are really working on it, and we are trying to leverage all our HPC expertise in order to extend the possibility of this simulation beyond the barrier of 30 qubit and to scale exploiting as we can our HPC infrastructure, as simulating a quantum computer require exponential resources that are displayed here like lines in a logarithmic graph. And so we see that as far as we can fit all the computation in the multi-GPU and avoiding to saturate the memories, we can have a flattening of the curve that depicts the computational resources rise. But anyway, more work is needed, further work is needed in order to extend the capability of simulating more and more qubits on our infrastructure. So I'm done now. Thank you so much. The floor is yours, Lidia.
Thank you very much. Okay. I shall adjust for the conclusion. Okay. Very good. So, after all, we have said, we wonder, ask us, okay, where do we go from now? Which are current perspective and the future challenge at CRS4 to solve a real problem using QC and HPC? Our goal is to advance the state of the art in HPC and QC simulation application, faster the technological transition toward hybrid computing, HPC and quantum computing and quantum communication through the development of an innovative method and approaches for study the system and complex processes based on advanced methods of analysis, data acquisition techniques, machine learning techniques, and artificial intelligence. The CRS4 aims to improve the efficiency of the processes and complex system understudy by allowing through a significant reduction in calculation time. This is very important. For the reduction of the environmental impact of the calculation system. Now, artificial intelligence and big data are already fundamental tools for scientific research industry, while supercomputing and quantum computing help to delve into scientific challenges, keep pace with an increasingly complex system. As we have seen, quantum computing offers significant opportunities for the development of new technologies because it allows the computational solution of a very complex problem that traditional computational technique cannot solve. Although is in the early stage of its development, quantum computing, thanks of its calculation method, can provide an effective solution for specific problem. Quantum computer can, in fact, solve some problems that currently cannot be addressed, and with time, there are a lot of new examples for their practical application are emerging. Gaining a quantum edge through the integration of quantum computing optimization algorithm running on high performance computing system. The hybrid direction is exactly what leading European computing center are taking to create a European ecosystem in quantum computer connect of leading supercomputing in Europe. The main objective will be to limit the latencies of our hybrid algorithms as much as possible and further investigate the potential that will arise from the combination of high performance computing and quantum computing. Our goal, the CRS4 goal, is to host both quantum computing and HPC infrastructure in the same place, accelerate the hybrid software development process, and perform applied R&D to get the most out of the underlying software and hardware. The objective of CRS4 is to continue working with the application and acquire a quantum computing node. This is very important. We hope that we will have in the future a quantum node at CRS4 at the service of our researchers, and to become one of the reference point for the development of quantum computing application in Italy. We are not people that would like to have just the node, the quantum node, but we would like to be a reference point for the application in quantum computing. As mentioned above, our goal is to study and develop applications that enable the use of quantum technologies, high performance computing and edge computing, which is the widely used in application in different types. We are open for collaboration, to collaborating and joining force to enable a future of quantum computing. Thank you all for your attention. Thank you very much to my colleagues for their presentation. They were really, really interesting. And here you can find our referencing if you would like to contact us. Have a good day. Thank you very much.